Okay, hello. And so let me go ahead and figure out what's due this week. We have, of course, our homework for the first module is due, well, module 5, the stereochemistry, is due today at midnight, so don't forget that. And then the module 6.1 will be due next Friday, and I'll start 6.2 actually on Monday. And then what we'll end up doing is probably moving that group activity 3 up to maybe Friday the 16th, but I'll give you a heads up on that on Monday. So I really want to get into that, and I thought I had more slides than I do, but I don't, so that's going to be a great time to do it. Let's see, what else do we have here? So that's in the homework is due next week. One is due October 16th, and the second one is due October 19th. So the only thing you have to do is get your homework assignment for chapter 5, module 5 in tonight by midnight. Okay. Any questions about that or what we're going to be doing? Well, if you do, go ahead and put them in the chat or.
I have a question.
I'm sorry, what?
The chapter 5 homework that was originally due Wednesday, is that the same one you said that it's due tonight?
Oh, actually it was due on Wednesday. Yeah, you're right. I'm sorry. I changed it to Wednesday, not Friday. I apologize.
Oh, okay.
Yeah, it was due. So you are correct. I haven't graded it yet. So, well, I haven't gone and looked at the grades yet. So that's, well. Okay. So that being said, let me go ahead and continue on. Let's get back to our 6.1. And I'm going to pull up my screen here on a slide we just finished, but I wanted to start there again. Okay. So what we've learned so far is there's different patterns we should see in our chemistry as we go through. There's the adding across a bond, there's breaking a bond, there's a couple different ways to break a bond, etc. Okay. And then we knew that now we've also looked at the fact that there's some energy associated with this, and that gave us what these energy diagrams are. Now, the important thing about the energy diagrams is knowing the three components, the three components on this one-step reaction being the starting energy and ending energy. And therefore, the difference here is going to tell you whether it's giving off heat or absorbing heat for the system. The second thing we see is this activation energy. And that's the energy required to make that transition state happen. And transition state is the third thing we have to worry about here. So if you have enough energy, you can get to that point where you are starting to break a bond and make a bond at the exact same time. And when they cascade to products, you end up with a different energy, different bond energy than you had starting with. And it's either more energy than you started with, and therefore it's endothermic because you absorbed energy, or it's less energy than you started with, and it gives off heat. It gives off energy as heat, and that's exothermic. Now, when we go to those two-step reactions, we add a complication in the fact that we still go through we still have our product starting at one energy and ending at another energy. And they're still endothermic or exothermic, depending on whether this is below the starting materials or above the starting materials. However, we have a new thing that we have to identify here. We have our activation energy to create an intermediate. So this intermediate here is unique to two-step reactions, okay? Now, we then have a second activation energy, and it's usually smaller than the first activation energy to get to products, because you have to take your intermediate you formed and react it with something else to give us our final products, okay? So in the one-step reaction, we have those three important things: energy of the reactants and products, the energy of getting to that transition state, and the transition state. In the two-step mechanism, we add the intermediate as something that has to happen and a second activation energy. Okay, so that being said, these are common patterns we'll see over and over and over again when we talk about our reactions. And these reactions will be labeled by the number of molecules required during the transition state. And we'll see that in the lecture starting next week. Okay, So starting with that, let's go ahead and we talked a little bit about the energy and the enthalpy and the Gibbs free energy. And the key here is that the enthalpy or the change in enthalpy of the reaction is proportional to the change in Gibbs free energy, and with the caveat that there's a temperature and entropy component. Most of the time, the temperature and entropy component are small enough that they are just directly proportional. And so we look at that as helping us to see whether or not we have that change in energy or that change in potential energy in the reaction. Okay. Now, moving on to a different topic, we have an idea of what we call kinetics. Kinetics is not about the change in energy, it's about the speed of the reaction. And therefore, the speed of the reaction is actually determined by the height of the activation energy barrier, not where the starting materials and products are. It's all about that height to form that transition state, okay? So in kinetics, the higher the barrier, the slower the rate, the lower the barrier, the faster the rate. And it has everything to do with the number of molecules that have the available energy to do it. Okay. So in the case of that, we want to think about, you can think about it as, as you start the reaction going toward your transition state here, imagine it being a kind of like a mountain, and you have to hike up that mountain. And let's say you hike up the mountain and you didn't eat breakfast and you lose energy. And so you got to stop and gain a little more energy by eating a power bar. And then that gives you a little more energy to climb a little higher. And then you need a little more energy to get to that top. Okay. Once you get to that top, you're happy and elated, but then it's much easier for you to transition back down to products now that you've reached that transition state. So the slow part of the reaction is that climb up to the activation energy until you reach that transition state. Once you reach that transition state, everything is, quote, downhill from there and is much easier. Okay. So if you think about that activation energy, is you have to have enough energy to get enough of those molecules to get in that position where they can form that transition state, then you can form products. You cannot form products until you have molecules that are close enough together and have that energy. Okay. So that being said, even both of these reactions are both exothermic. See, the reactants and the products are starting and ending at the exact same place. However, the first reaction happens faster. The one here on the left happens faster because our activation energy is lower. Okay, it takes less heat and more molecules have the heat that's available to it to get to that transition state. And if you can get to that transition state easier, the reaction happens faster because this is the slow part is coming up here, and then this is the fast part going down here. So if you have a bigger slow part, it slows the reaction down. Okay. And again, we're not changing anything about, the reactants and products here. Now, things that can increase your rate are things like concentration. The higher number of molecules you have available to make that transition state, the faster the reaction can go. Okay, and if you think about it this, if you have 10 molecules that can form that transition state, there's gonna, and it, you have enough energy that it happens once a minute where the two molecules get close enough to do it. Now let's double that. Now you have 20 molecules. Now you have two molecules every minute that can get close enough to react. And let's double it again. Let's turn it into 40. Now you have 4 molecules every minute. So every time you increase the concentration, you increase the rate of the reaction because you're increasing the number of possible chances that the two molecules reacting can hit each other. And therefore, once they hit each other or form that transition state, they cascade down the hill and form products. Okay. So what else can help the rate? So a lower activation energy speeds up the reaction. Concentration speeds up the reaction. Well, it turns out that temperature can also speed up the reaction. And if you think about it, that makes sense because let's say your reaction is endothermic or exothermic, it doesn't matter, but you have to add energy to get up that activation barrier. So by adding more heat to the system, you have more molecules that have more energy, and so more of them can get up to that transition state faster, and therefore the rate goes up. Okay, we haven't changed our number of molecules, but we're increasing the number of interactions because they're moving faster. And the rule of thumb on this is that for every 10 degrees you raise a reaction, it doubles the reaction rate. Now, this is just an average over many, many different reactions. So an individual reaction might not be double, but in general, this tends to work. So if you were in lab and you were making an ester and you started at 50 degrees and it took about an hour to make it, if you increased that by 10 degrees, ran that reaction at 60 degrees, it would take half as long to do the reaction, assuming the same concentration. So we have activation energy controlling our rate, we have concentration controlling our rate, and we have temperature controlling our rate. And increasing any of these things, increasing the temperature or the concentration will increase the rate. However, increasing the activation energy decreases the rate because it's a higher barrier to get to that transition state. Okay, so let's look at why that temperature really helps. So if we think about the statistical probability of a molecule having enough energy, or the shared energy that's in that reaction system. So let's say our top line here is at 50 degrees C, okay? And we have 1,000 molecules in there, okay? So if we're dividing up all the heat available to those 1,000 molecules, the average energy of any one of those molecules is going to be some energy. And then some of them are going to be not moving at all, and some of them are going to be moving a little bit faster, okay? So now let's raise that temperature up to 60 degrees, okay? So now your average energy has increased right here, and you've also have more molecules that are higher in energy. Okay. So the next thing we have to think about is, well, where's my activation energy? So my activation energy can't be down here because the reaction would have just already been done. Okay, and so in this case, our activation energy is here. Okay, so that means in this first case at 50 degrees, 95% of our molecules don't have enough energy to make the reaction happen. Okay, but this little portion here, if we integrated the area under the curve here, that little portion of the molecules have enough energy to react, and therefore they do react, okay? And if the reaction's exothermic, their heat is then given back to the system, and more molecules go above that barrier, and then so it keeps going until all of your reactants have gone to products. Now, if we just raise that 10 degrees right here, we have a higher average temperature, but our activation energy has not changed, right? If we have that higher average, then we have a higher number of molecules that are above the activation energy. The more molecules above the activation energy, the faster the reaction goes, okay? So that's why just that 10 degrees is enough to double the reaction rate, because you have so many more molecules available to you that have the energy necessary to react. Okay, so what we're going to learn here is all the reactions for the rest of the semester are controlled by two things: energy and sterics. Okay, so we've introduced energy to the system. Now I want to introduce sterics to the system. Okay, what sterics means is how bulky the groups are where the reaction is supposed to take place. Okay, so when we talked about acids and bases, I told you that we have a Lewis acid and a Lewis base, but we also had a special name for them. One is called a nucleophile, which is a Lewis base. Now remember, a Lewis base has electrons that it can share to make a new sigma bond. Okay. Electrophiles are the opposite of that. They are Lewis acids, okay? Meaning they lack electrons, or they have a partially positive charge somewhere on the molecule. And so when a nucleophile comes in to interact with an electrophile, and in this case, we're doing it in a one-step reaction, it has to come in opposite from where the other group is going to leave. We have to form the new bond exactly 180 degrees from where we're breaking that old bond, okay? Now, if you have to have that happen at that 180 degrees, that means you are really worried about what groups are attached here. Let's say all three of these are hydrogens. That would be the ideal smallest atom we can put on that carbon. We would consider that reaction to have no steric hindrance because the hydrogen's the smallest atom we can do, and therefore our nucleophile here can come in with its electrons and form its new bond and have this leave. Okay. Now, what if we take one of those hydrogens away and just add one methyl group right here? So look at the physical difference between the hydrogen and the methyl group. It takes up more space. That means that just having that one methyl group is going to slow the reaction down. Okay. And let's add another group here. And another group is going to slow that reaction down even more because we have a smaller window of opportunity for that incoming nucleophile to attack at 180 degrees from where the leading group is going to leave. Now, that's just the steric interaction on the substrate. We call this the substrate because this is where our new product's going to be. Let's look at the steric interaction on our nucleophile. Okay. As our nucleophile gets bigger and bigger, it also affects the reaction. Okay. It slows down the reaction as this gets bigger because of its, these are starting to crowd out the space where the lone pairs, remember these have lone pairs here, those are crowding out the lone pairs, changing which lone pair can effectively make that new signal bond. Okay. So energy and sterics control most of our reaction rates. Okay, so let's talk a little bit more about that. Okay, and so if our rate is controlled by energy and heat and concentration and sterics, we can actually develop a mathematical equation that lets us figure out how these things are interrelated. And so we call this the rate equation, or sometimes it's called the rate law. And basically it's a reaction, it's a way of telling us what's important for the reaction to progress at a specific rate. Now, most rate equations, the actual rate law is actually measured. It's not theoretically derived. So the actual K value is measured. So don't try to take anything away from that. But our rate in general is our factor right here, when we'll talk about that in a minute, times the concentration of the nucleophile and the substrate. And that's in the case of this SN2 reaction, okay? And we're gonna talk about SN2 reaction a little bit more in the next module. However, the idea is in an SN2 reaction, both the substrate and the nucleophile are forming that one-step reaction. So they both have to be in the transition state at the exact same time. Therefore, it's dependent upon their concentration. Now, that being said, we can actually kind of help figure out how to back out that rate constant, that measured rate constant, and actually derive what the activation energy of the system is, plus the pre-exponential factor, which is kind of related to the type of reaction. So the idea is our measured rate constant here is equal to some frequency factor or pre-exponential factor, and that's related to the type of reaction, times E, which you may know from its mathematical terms, over the activation energy over RT. R is the gas law constant, and T is the temperature in Kelvin. Okay. So as T gets very big, our rate law gets big. As E gets very big, our rate law goes down. So a smaller E and a bigger T makes the rate go faster. So how do we use it? Well, we use it mostly in the the term where we have it in this form right here, where we're looking at the substrate and the nucleophiles concentration. So if we look at our rate law, if we just had our rate is equal to some constant, it's measured, it doesn't matter, and we increase the rate and we increase the concentration of the two components here, we will increase the rate of the reaction. So we saw that directly when we said what affects that reaction. So the rate law, that's why concentration appears in our rate law, because it's important. Now, when we look at other reactions, we'll see that maybe only one of the components is important for the rate law. So only changing the concentration of one component will affect the rate, make it go faster or slower. So it's important to look at our rate law as our constant, which is measured, and then what components are required in the reaction rate by whether or not we take into account their concentration. Okay, so that's just general reactions. And in the first step, we showed that first step reaction, that first one-step reaction, that it had just one little hump and then it went to products, okay? Well, that's true. And then that two-step reaction where it forms an intermediate and goes to something else, that's true too. However, we can get much more complex reactions happening if we use a catalytic system or a catalyst, okay? Most of the time, whenever a catalyst is used in a system, and it can be something as simple as hydrogen, as an acid or a base, or it can be something very complex like an organometallic compound, okay? The whole purpose of the catalyst is to lower the activation energy of that first transition state. So in this case here, let's say we had just an SN2 reaction, nice simple one-step reaction. It has to get to that transition state where the group's coming in and the group's leaving at the same time. However, if we used a catalyst for the system, we could lower that first activation rate, which would give us some intermediate, which would then again transition and transition until we finally got to the exact same product. So our energy diagrams get a little more complex with catalyst, but it demonstrates why catalysts are used because it lowers that activation energy and gets you to products faster. All right, questions on rate constant and these energy diagrams? So, all right, great. So that brings us to kind of a rule of thumb, also known as the Hammond postulate. The idea here is that in a reaction, if the transition state looks more like the products, if the transition state looks more like the starting materials, the reaction is going to be exothermic, meaning that if you have the new bond you're forming is stronger than the bond you're breaking, you're going to give off energy. Okay, so, and the opposite is true. If you had a reaction where you actually, so in this case, we say it's an SN1 reaction. This is that happening once. In this other reaction here, you actually want to break the bond first. So you're actually looking closer to products. If you're looking closer to products before the reaction happens, then it tends to be an endothermic process. Okay, so in this case here, let's look back at the SN2 type reaction here. Basically, the idea is that you have to start forming your new bond before your old bond starts breaking. Okay, so you're looking like your starting material. Those tend to be exothermic products. If you actually have to have your nucleophile come in and almost start forming the bond before your bond starts breaking, then your bond has to break first before you start forming that, then it is endothermic. You have to put more energy into the system before you have that product formed. Okay, so there's also a nice little video, I believe, in the reading about this. All right, so what we've talked about so far is energy and rate, okay? Energy and rate are related to but different than kinetics and thermodynamics, okay? So kinetics are the rate of the reaction. Thermodynamics are the heat or free energy given off or absorbed in the reaction. So kinetics are more related to rate. Thermodynamics are related to the change in energy or the change in free energy. Okay. So they are different and they don't necessarily have to be one or the other, they can be both. Okay. So I want to make sure you understand that there are different components and they are not mutually exclusive. Okay. So the idea is that, okay, let's take this example here. Okay, so this is two different reactions. Okay, so we start with the same components, but we end up with different products here. Okay, so if we have A and B and we go through this transition state first, this is our number one transition state. It's a lower transition state, meaning that it's going to go faster, right? Because the lower energy of activation makes the reaction go faster. And once it goes through that lower activation energy, our products are down here, okay? And so the difference between our starting material and products is this change in enthalpy here, and it shows it to be exothermic, okay? So let's say instead we maybe used a different material as A and B, and it took a higher activation energy to get it to go. So kinetically, this reaction is slower than the first reaction because of that higher kinetic energy, okay? And when we come down here to look at its products, it gives off less heat during that, meaning it's also less thermodynamically stable, okay? This has a lower potential energy and therefore is more thermodynamically stable, which means this first reaction here is kinetically favored and thermodynamically favored over the second reaction. Okay. Is that always the case? No. Okay. So what would it look like if those two were somehow in competition? Okay. Well, the diagram would look a little different here. Okay. So in this case here, what we have is our starting materials here. And if we look at our first reaction, is this a lower one here? And it took a less amount of energy to go. So this was the faster reaction right here. This line is the faster reaction because it took less energy to get to that transition state. But look at the products, okay? The products gave off very little heat. There we go. The products gave off very little heat, okay? There's a very small difference in the products and the reactants, okay? Now, what if it went through a different transition state? We could change A and B such that it took a higher activation energy here. So now this is a slower reaction because of that higher activation energy. However, the products ended up being at a lower potential energy. So it's a slower reaction, but it's more thermodynamically favored. So it's kinetically disfavored, but thermodynamically favored, where this one is kinetically favored and thermodynamically disfavored. Okay, so so that's how you can tell the difference and watch the difference between kinetic and thermodynamic. So in general, the rate of the formation of the most stable product will be faster than the formation of the less stable product, okay? So most of the time, what we'll see is the lower activation energy ends up giving us the lowest potential energy. However, that's not always true, but for most reactions, we can say that that's probably going to happen. Okay? And it's because it follows a pathway that gives the more stable, lower energy transition state. So if you have less energy in there, then you have a small free energy of activation, and therefore we have a smaller energy to go. So it is faster. A smaller activation energy is faster, but then that change in the free energy at the end is usually larger than if it was not going through that pathway. So in general, most reactions are kinetically and thermodynamically clear, but that's not always true. And looking at the reaction diagram helps you determine whether it's true or not. Okay, so that being said, we can have two different types of reactions. We can have a kinetically controlled reaction or a thermodynamically controlled reaction. So in a kinetically controlled reaction, we typically think of that as that there's enough kinetic energy to overgo the activation energy. There is just enough activation energy to go at that faster rate, and the condition produce the less stable product. Okay, so if you can go over a smaller activation energy and come up with less stable products, you are kinetically controlled. The smaller the activation energy, the faster the reaction, right? So if you go through a particular transition state which allows it to form those less stable products, you are in kinetic control. Now, at higher temperatures in particular, you now have enough energy to go both over your low energy and your higher energy activation energy. So if you do that same reaction at a higher energy, you now have enough to go through the first pathway, but you also have enough energy to go through the second pathway. And the second pathway leads to the more stable product. Okay, so the one with the greater exothermal. If you have enough energy in that system to go through that higher energy barrier to form the more stable product, you are now thermodynamically controlled because you're making the more thermodynamic product. Okay, so this is typically, one of the ways to do this is control it with temperature or with catalyst. Okay, so questions on energy diagrams and kinetic and thermodynamic control. Okay. Remember, we can see what's happening on our energy diagram here. Okay, on this reaction here, now let's use the different definition that we just had. This reaction is done at 50 degrees and doesn't have enough energy to go through this second transition state, and therefore makes the less stable product. Okay, so this would be kinetically controlled reaction. Let's say we do this one at 100 degrees. Now we have enough of the energy to not only go past this transition state, but go to a different transition state. And if it has enough energy to go to this different transition state, this different transition state actually makes the more thermodynamically stable product because it releases more heat. And therefore, this reaction is thermodynamically controlled. And the first curve here is kinetically controlled. So that's where the lower temperature can give you the less stable product, and the higher temperature can give you the more stable product. Okay, so those are the general concepts of kinetics and thermodynamics we'll deal with. Remember, it's temperature, activation energy, and concentration affects them the most. Okay. So now we're going to transition to our last topic for this section, which is nucleophiles and electrophiles. Okay, I introduced the topic a couple times, and I introduced the topic when we talked about Lewis acids and bases, but I want to go and get a really good, clear picture in your head about what nucleophiles and electrophiles are, because we use these terms to determine which molecule is going to be coming in with the electrons to make that new bond that we're going to make, or break a bond that we're going to make. So in general, a nucleophile is some atom that is an electron-rich atom that is capable of donating electron pairs. Okay, so imagine things that have a negative charge or a lone pair that can come in and use that negative charge or that lone pair to create a new sigma bond. Okay, Lewis bases are nucleophiles. Remember, they have that lone pair of electrons, those electrons willing to make a new sigma bond. So nucleophiles are Lewis bases, and they're commonly seen in things like alcohols because there's two lone pairs on alcohols. Amines, there's a lone pair on amines. Alkenes, alkynes, and aromatics. Why would that be? Oh, they have pi orbitals. They have pi bonds. Pi bonds, because they're above and below the atoms, are highly electron rich and can be nucleophiles. So alkenes, alkynes, and aromatics can be nucleophiles. And of course, anything with a negatively charged species is typically a nucleophile. Okay, so do we understand what a nucleophile is? It's any electron-rich atom, can be carbon, can be other things, can be oxygen, but it is capable of donating those electron pairs. And so that's why we draw them to be the same as Lewis bases. Okay. So that being said, the opposite of this has to be the electrophile. The electrophile has to be an atom that is electron deficient or is willing to accept a pair of electrons. And we can think of the proton or the hydrogen that gets transferred, or a carbocation for this, okay? Now, it's anything that can accept that pair of electrons to make a new sigma bond, which means our Lewis acids tend to be electrophiles. And classical examples of electrophiles are alkyl halides, because you can lose a halogen and make that happen. Electron deficient atoms like boron or carbon with a positive charge, and then positively charged species. The most readily available to us would be something like a carbocation or a positive charge on carbon, or some kind of metal, okay, or hydrogen. Okay, so what does this look like? Okay, so again, these are centers. These are the atoms that are going to be where the new sigma bond is going to be formed. Okay, so we can actually have carbon act as either one of these. In this case, it's acting as a nucleophile. The reason it's acting as a nucleophile is that it's more electronegative than the lithium, meaning it's a polarized bond. So the carbon here is partially negative and the lithium is partially positive because it's a polar bond. Okay, so there's more electron density on the carbon, therefore it is a nucleophile. It is looking for a positive charge because it has extra electron density. Okay. Now, the other classical one is like a Lewis base. Anything with a lone pair that can share these is a very common nucleophile, and that's going to react at that atom. Okay. The other system that we'll look at a lot is the nucleophilic site of the pi bond. Basically, this is where the electrons are, and they are willing to come out and grab at something that has a positive or partially positive charge to react with. Okay. So those are the common nucleophilic sites we're going to see, and the things that are actually, the site is the actual part that's going to be doing the nucleophilic attack. Now let's look at the other side. Just like here, where we have a polar bond in carbon, we have a polar bond between the carbon and the fluorine, but it's going the other direction. The fluorine is partially negative and the carbon is partially positive. So that means it wants electrons. So it is the electrophile. It wants the electrons. So let's say we had a very polar bond here and we broke that bond first. Like in that two-step reaction, the first thing we did was break a bond, and we formed this right here. This is a carbocation. So it is lacking electrons. It needs 2 electrons to fill its octet, and therefore it is ready to react with any nucleophile in the area. Another classical one is this Lewis acid right here, boron. Boron, that molecule itself is neutral because of its electronic structure. However, it doesn't have a full octet. So it's willing to accept electrons to fill its octet, even though it's going to form a charged species. Okay. So nucleophiles are looking for positive charge, meaning they have excess electrons or lone pairs. Electrophiles are partially positive or positive charges, or are electron deficient and are looking to fill that deficiency with electrons from somewhere else. Okay, so let's start looking at a concept we call electron pushing. Okay, electron pushing gives us an idea of which electrons we're going to use in reactions to create our new sigma bond. Okay, so this technique is to show you the electron started on one atom and ended up being shared by the two atoms to create our new bond. Okay, so in general, when we do this, we have a double pronged arrow here saying 2 electrons are coming out to form a new sigma bond. And in this case, we're looking at something like this. Okay, now this is our nucleophile, and look at it, it's a classical nucleophile. It has lone pairs and it has a negative charge. Okay, so it is looking for positive charge to share that negative charge with so it can make a neutral molecule. Okay, and in this case here, we have a classical electrophile. It has a positive charge. It is needing electrons. And so it is ready to react with any lone pair out there to generate a new sigma bond and fill its octet. So now the great thing is after we react, our bromine has its octet and our carbon has its octet. So they're happy. So that's the driving force of having this nucleophile attack the electrophile. And this is how we note where the electrons were and where they became. They became this new sigma bond. Okay. So there's another way we can do this. Okay. And we can have notice in this species, we had them both charged, negative and a positive charge. Okay. So the other kind of electrophile we have is a polarized bond, right? So in this case here, we don't have a positive charge, but we have a partially positive carbon. Okay. Because of that polar bond, the oxygen is more electronegative and pulling some electron density up toward it. Okay. So that being said, we also have an oxygen with a negative charge. So that makes it our nucleophile. And in this case, our nucleophile is going to use one of its lone pairs to come in here and attach to that electron deficient carbon to create a new sigma bond. However, carbon cannot have 5 bonds. Therefore, that pi bond has to do something such that we only have 4 bonds to carbon. And in this case, what happens is the electrons from the pi bond reside on the oxygen. So notice we started with a negative oxygen here, and actually our transition intermediate here also has a negative charge on oxygen. Okay. So when you have to do this, now in the previous one we had a negative and a positive and it went to a neutral species. Okay. Well, this is a two-step attack because we typically want to somehow get back to a neutral species. Okay. So however, we cannot break the rule about having 5 bonds to carbon. So we cannot draw it where our electrons come in and make a new bond, and we end up with 5 bonds to carbon and the negative charge on carbon. Okay. So we have 10 electrons around carbon, which is not appropriate. However, we do have 8 electrons around oxygen, 8 electrons around carbon. Everybody has 8 electrons around them. So this fully qualifies its octet. It's 8 electrons around everything, but we now have a formal charge on oxygen. And there'll probably be some other reaction that happens such that we get rid of that negative charge. But we'll get to that when we're actually doing the reaction. But the key here is that we must maintain octets. We must maintain not having more than 4 bonds to carbon during these species. All right. So one of the reactions we showed was that you can actually start with breaking a bond, okay? And that was one of those patterns we saw. When we break a bond, we actually already have the electrons in our sigma bond, and both of those electrons are going to leave with the negatively charged species. And then we have the positively charged species being the other system. Okay. And this is what we call heterolytic cleavage. If we have one electron leave with each species, and we're going to talk about that in module 10, radicals, that's a different type of reaction. But up to that point, we're going to talk about where both electrons leave with the negatively charged species, and we have a cation being formed. Okay. But again, the 2 electrons from the sigma bond are leaving with a negative charge. So another pattern we'll see is the transfer of a proton. Okay. So we have a pattern where a nucleophile and electrophile attack each other. We have a pattern where a nucleophile attacks a polar bond and creates another species. Now in this one, we have the formation of the transfer of a proton to switch electrons from one atom to another. Okay. So in this case here, we have just a ketone, and it has these 2 lone pairs. So that lone pair is acting as our lowest base. Okay. And so I think I've said this before, but you never actually have a free proton floating around in solution. Okay. There's always electrons around your hydrogen. It's just where those electrons are coming from. Okay. So what's happening is these 2 electrons are reaching out and starting to surround this hydrogen. And when it does that, the 2 electrons that are used in that sigma bond with the other species go back to the other compound. And in this case, it's the positively charged oxygen. When it does that, we created our new sigma bond with our system, and the positive charge has actually been transferred to this oxygen now, and we have our neutral species over here. Notice whenever we transfer a proton, the one that's acidic goes neutral, and the one that was the base now has a positive charge. Okay, because our base is being protonated, our acid is being deprotonated. Now, it doesn't only happen with water. It's very common to see this in protonated alcohols. So in this case, we have the oxonium ion. This is where we have just an alcohol that has a proton on it, and we can get rid of that by adding some kind of base to it. In this case here, because we had a positive charge and a negative charge, but instead of making a new, so we're using this as our nucleophile, and this is our electrophile to make our new sigma bond right here to deprotonate our species. So we've just transferred a proton from one to the other, and we end up with 2 neutral species. Okay, so we had a positive and a negative going to 2 neutral species. And so it's just the transfer of a proton. This is very common. In fact, if you ever see an acid catalyzed reaction, first step in that reaction is going to be to transfer that proton to something. Okay, so I think I'll ask if anybody has any questions. So in this chapter in particular, we're looking for patterns. We have this bond breaking, bond forming, elimination to form a double bond, substituting things. Those types of things we're going to see again and again and again. And then by looking at our Lewis dot structure and seeing where the electrons are coming and going, we can see what are possible reactions and what are possible products. All right, any questions? Okay, so on Monday, we're going to start with carbocation and carbocation stability, and then we're going to get into SN2 reactions. And I'll have those slides up over the weekend so that we'll have those available to us by Monday. Okay, I'm going to go ahead and stop recording and let you freely ask questions.